Hello, welcome. In this short video, let us look at an equality commonly used in Kramer-Rao bound. That is, we want to prove that the expectation of the negative second derivative of log likelihood function is equal to expectation of the first derivative of the log likelihood function whole square. That is, this is a common equality that is used in CRB theorem. So, here x is the sample of observations, theta is the parameter that we are trying to estimate, and expectation is taken with respect to the probability distribution of x. So, let us start with the LHS. This expectation of negative second derivative with respect to theta of the log likelihood function, which is equal to expectation of minus derivative with respect to theta of the first derivative of the log likelihood function, which is equal to expectation of minus dou by dou theta of 1 by the probability distribution, that is 1 by the likelihood function multiplied by derivative of the likelihood function. Now evaluating the next derivative, and since we have two terms in the product, we have to use in the formula for the derivative of the product of two functions. That is, we have the first function is 1 by the inverse, the 1 by the likelihood function, and the second one is derivative of the likelihood function. So we have expectation of minus the derivative of the 1 by probability of x given theta, that is 1 by the likelihood function, which is minus 1 by probability of x given theta, that is the likelihood function, multiplied by derivative of the, of course there is a square here, that is minus 1 by square of the likelihood function multiplied by derivative of the likelihood function, and then we have another derivative of the likelihood function, and then the second term is minus 1 by the likelihood function multiplied by the derivative of this first derivative, which is second derivative of the likelihood function. So we are left with expectation of minus or minus is plus derivative of the likelihood function, and there is two terms, that is the derivative of likelihood function repeats. So we have square of the first derivative of the likelihood function, and then we also have square of the likelihood function in the denominator, and then we have second term, which is expectation of minus expectation of the second derivative of the likelihood function divided by the likelihood function itself. So this is equal to, by using the definition of expectation, this is integral multiplied by the integral of the likelihood function multiplied by the probability distribution of x multiplied by the first derivative of the probability distribution whole squared divided by square of the probability distribution. The integration is with respect to x. The second term is integral the probability distribution of x multiplied by 1 by probability distribution of x multiplied by the second derivative. And the integration is with respect to x. Clearly, the first term becomes integral first derivative of the probability distribution whole square divided by the probability distribution of x dx, and the second term, it is the second derivative of the integral of the probability distribution of x dx, and since this is equal to 1 and the derivative of a constant is 0, so we have the second term basically vanishes. So we are left with integral square of the first derivative of the probability distribution with respect to theta divided by probability of x, the distribution of x dx. The second term is gone. So this is equation 1. Now let us begin with the RH. That is starting with this term, that is expectation of first derivative of the log likelihood function whole square, which is equal to expectation of 1 by probability of x given theta into the first derivative of the probability of x, the probability distribution of x, whole squared. And this is equal to, by definition, probability of distribution of x with the parameter theta multiplied by probability distribution of x with the parameter theta, that multiplied by 1 by square of the probability distribution multiplied by the first derivative of probability distribution whole square dx. And clearly this is equal to integral first derivative with respect to theta of the probability distribution squared the square of this first derivative divided by the probability distribution, and the integration is with respect to x. So this is expression 2. You can clearly see that the result in equation 1 is exactly same as the result in equation 2. Therefore, expectation of the negative second derivative of the log likelihood function is equal to expectation of the first derivative of the log likelihood function whole squared. Thanks for watching.